So next we will start on one very important type of indexing, which is the tree based indexing. And we will cover two important structures in this, the B tree and the B plus tree. So these are for indexing the data on the disk. So these are secondary storage, or the disk is sometimes called the secondary storage. So these are disk aware designs. And I am assuming that you are familiar a little bit with the binary search tree. So this is essentially a binary search tree built for the disk. So if you recall the main the main design of a binary search tree is that corresponding to a node, the data is divided into two parts, and the left subtree of that node, the left child, gets all the data that is less than the key that is stored in the node, and the right subtree or the right child gets all the data that is larger than the key that is stored in the node. So that is the binary search tree, and we will build upon the BST. So that is the binary search tree, and the B tree and the B plus tree builds upon that. And how is it stored? So the B tree, let us take the B tree, there is an order corresponding to a B tree of a particular order. We will see what the order is. Suppose the order is theta, has the following properties. First of all, the B tree is a balanced structure, and balanced, and all leaves are in the last level and final level. All leaves are in the, so balanced meaning all leaves are in the same level. So this is the balanced. Then the root node, there is a root node, has at least one key. It must contain, of course, at least one key. Any other node, every other node will have between theta to 2 theta keys. So it will have number of keys which is between theta to 2 theta. And a node with k keys will have k plus 1 child pointers. So the internal node design of a B tree looks like the following, is that there is a key, let us say key 1. Now corresponding to key 1 there is a child pointer 0, and then there is a child pointer, there is a record pointer 1 corresponding to the key 1, and then there is a child pointer 1. So this goes on. So child pointer 1, then there is a key 2, then there is a record pointer 2, then there is a child pointer 2, etc., etc. It goes on like this till there is about key k, let us say, then there is a record pointer k, and then there is a child pointer k. So this is the structure. This is a B tree internal node with k keys. So let us try to understand this. So there are these k keys. This is key 1, key 2 up to k key. Corresponding to each key, the record pointer, so this is a pointer that stores the record of the corresponding key, is stored next to it. So there are this k such record pointer and key pointer, and then there are k plus 1 child pointers, and the child pointers, this follows the same idea as the BST. So this child pointer contains all the keys that is less than this key 1. This child pointer contains all the keys that is greater than key 1 but less than key 2, and so on and so forth. It goes on all the way. So this is everything that is less than key 1, and this is everything that is greater than key k. Technically correct, this has to be less than equal to, so on and so forth. But that is the whole idea of a B plus tree, and it is organized in that entire manner. And then there is an order theta that is mentioned as part of the B tree. So every internal node must have between theta to 2 theta keys. It cannot have anything other than, it cannot have less than theta keys, it cannot have more than 2 theta keys. So there is a term called the branching factor or the fan out of a B plus tree is therefore it must have between theta to 2 theta keys. So, the branch out must be at least theta plus 1 and it is at most 2 theta plus 1. So, the branching factor of the fan out is the number of children that one node can have. So, in this case of k things there are k plus 1 children. So, that is a B tree. Now, let us move on to what is a B plus tree. The B plus tree is very similar, but with one important difference. So, the B plus tree is a very similar structure, but there is one important difference with the B tree. So, if one draws the internal node structure of a B plus tree, one can understand the difference. So, this is a key 1, then corresponding to this there is a CP0, then there is no record pointer. So, that is a very important difference. So, then this all goes on, then there is key k and then there is a child pointer k. So, then there is no record pointer corresponding to a key in B plus tree. So, there is just a key and there is no record pointer. So, this is 1, 2 again up to k, and then there are this again k plus 1 children, and this again follows the same idea key 1 etc. But it does not have the corresponding record pointer. So, this record pointer k is not maintained inside the internal node. So, what does this mean is that these keys cannot be actual search keys, because if it is an actual search key the record pointer must be present. So, even if it is an actual search key, the actual search key must be stored only at the leaf level. This cannot be an actual search key, because no key is stored, no record pointer is stored. This is not a search key, this is just what is called an key to index. So, these are not real keys that are present in the database. This may not be real keys that is present in the database, these are just keys to index. So, that is a big difference between a B tree and a B plus tree. Now, again everything else remains the same as a B tree. So, it is balanced and everything is in the leaf, and it of an order, it can have an order theta. So, that means it can have between theta to 2 theta keys etc. of the same thing. Now, how is the order of a B tree or a B plus tree? How to calculate the order of a B tree or B plus tree? So, I mentioned that these are disk based design. So, where is the disk based design coming? How to calculate order is where the disk based design comes. This depends on the disk that is there. So, if you remember, the OS cannot access everything from the disk, it can only access data in terms of a page or block. This is called a disk page or a block. So, suppose the disk page or a block is some 4 kilobytes of data. So, it cannot access only 1 byte of data, it must access the entire 4 kilobyte of data from the disk to the main memory and then process that 1 byte or whatever number of bytes that is required to do that. And if you also remember, the main point of this physical design that we showed is to reduce the number of this disk accesses, the number of random IOs or the number of sequential IOs is the main point. So, it does not matter what is the time spent in the main memory, but the point is to optimize on the number of blocks that is read or written by the algorithms, the number of blocks that is accessed. So, since a particular page must be accessed from the disk, and since accessing the page meaning accessing all 4 kilobytes of data, it makes sense to pack in the disk page with as much data as possible. So, as much of means as much of 4 kilobyte of data or whatever is the size there, such that once that page is accessed, once that page is brought into memory, the entire data that is stored in the page can be utilized, and it does not require another access to bring in another data point. So, what I mean to say is that suppose the disk page capacity, so the disk page, suppose the disk page has a disk page capacity is of C bytes. So, then it makes sense to put in as many search keys as possible within those C bytes, because so one has to access these C bytes, one has to bring all these C bytes anyway, even if one search key is accessed. So, it makes sense to put in as many search keys as possible within this C byte. So now how to calculate the order? So order is the maximum number of keys that can fit, maximum number of search keys that can fit in a disk page. The order is calculated using that can fit in a single disk page. So that is the maximum that it can fit in a single disk page. And how to compute it? Let us say the disk page capacity is C bytes. Let us say the order is theta, and we will calculate what theta is. This is theta. And suppose key requires some gamma bytes to store, and pointer, the pointer to where the data is, requires some eta bytes. Fine. So for a B plus tree, what will happen is that this C must be greater than equal to 2 theta. So if the order is theta, then there will be 2 theta keys that can be stored. So 2 theta times gamma plus, there are no record pointers for a B plus tree. So this we are doing for a B plus tree. There is no record pointers, but there are 2 theta plus 1 child pointers. So which is eta. So this is the definitive equation for a B plus tree. So if you calculate, this comes out to be theta for a B plus tree, then comes out to be the following. It's C minus eta by twice of gamma plus eta, and of course one has to take the floor function of it. It is the maximum number that can fit it. This is how to calculate the order for a B plus tree. For a B tree, the same thing can be done, except there is something more. So there is a 2 theta of gamma. This is the number of bytes that is required to store the 2 theta keys. Then there are 2 theta record pointers. So one has to add this 2 theta times eta, plus of course the 2 theta plus 1 times eta for the child pointer. So this then comes out to be theta of B3, then comes out to be C minus eta, but this is 2 of gamma plus 2 eta. So these are the two important formula that we need to remember on how to compute the order of a B plus tree. How did we come to this conclusion? To repeat, is that it makes sense to read an entire disk page, so it makes sense to pack in as much data as possible within a disk page, because that is the least that the OS will read anyway, and the disk accesses are the costliest operations. So it makes sense to reduce the number of disk access operations, and once a block or once a disk place is accessed, it makes sense to pack in as much of that C bytes as possible. If theta is the maximum number of keys that can be done, then these two equations give a way of how to find out this theta. And we can take a simple example of how to do it. Let us compute this example. There is a page size. Typical page size is of the order of 4 kilobytes, 8 kilobytes, etc. Let us say it's 4 kilobytes. So this is 4 kilobytes, the page size. Let us say the keys take 8 bytes, and pointers, I suppose it takes 4 bytes. Let us assume this is the situation. Now how do we find out the B plus tree? The B plus tree can be used to the formula that is there. So this is the capacity. So if one computes this comes out to be 170, while the theta for B3 Now I want to highlight one important point here. You see that the order of a B plus tree is more than the order of a B tree. So it is in this particular example it is 170 versus 127. So which means that for a particular node there can be much more data packed for a B plus tree than a B tree. So which also means that the height of a B plus tree can be lesser than that of a height of a B tree, because assuming the same amount of data, since more amount of data can be fit within a node, less amounts of nodes are required, and the branching factor is also larger for this node. So which means that the height of a B plus tree can be less. However, what may happen is that in a B tree the search key is located higher up than the level of the leaf. So a particular search key can be located much faster with going all the way up to the leaf level. For a B plus tree there is no way, because the internal nodes do not contain the search key. Every search key is stored only at the leaf level. So to find a search key for a B plus tree, the search has to process all the way up to the leaf level. In general what happens is that the number of search keys that the B plus tree found without going all the way up to the leaf level is very low, and therefore what the database practitioners actually do is to build up a B plus tree and not the B tree. And even though one will find that the B tree index is being built, it is actually the B plus tree index that is being built for commercial databases and for other implementations of database systems. So it is the B plus tree that is the de facto standard. And that completes the B tree and the B plus tree thing, and that also completes about the tree based indexing. There are a little more left about the indexing, and one very interesting kind of indexing that can be done is called a Beet Map Indexing. So what may happen is that when the attribute domain consists of a small number of values, so a bit map or a bit vector can be employed to store all such values. So let us take an example to highlight what I am trying to say. Suppose there is a simple table which is gender and grade, and suppose this is male C, female A, female C, male D, male A. Now each of these gender has a very small attribute domain because it contains only male and female. So is the grade, it contains only A, B, C, D, and suppose that is the case, then one can employ a bit vector to encode all these values. So what one can do is to say that the male consists of the following manner. It's 1, 0, 0, 1, 1. Why is it 1? Because the first one is a male, the second one is not a male, the third one is not a male, fourth one is a male, fifth one is a male. Now note that 1 means it is a male, the 0 means it is not a male. It does not say what the value is, and for that we require this female coding as well, so which is 0, 1, 1, 0, 0. And although this looks like a redundant thing because it is complementary, because it has got only two values, it will not happen for A, because A will have this 0, 1, 0, 0, 1. B, none of the values is B, so it will have 0, 0, 0, 0, 0. Now note that for example here it is not A, but it does not say what the value is, and one has to go to C to find out that this is actually C, and D is simply 0, 0, 0, 1, 0. So how is this useful? So suppose a particular query is find all males, find male student who got D, find male student who got D. Now this is one only needs to do the take the beat map of M and do a bitwise AND with bitmap of D. So that is easy to do, and once that is being done, the answer comes out to be, so bitmap of M is this one and bitmap of D is this one, and once that is being done, this is the one that is highlighted. So it's the fourth student who is the male who has got a D. So bitmap operations are generally much faster and more efficient because the OS packs them in nice bite-sized order, etc. So that is why these are more can be faster. to complete the indexing scheme, this is how things are being done in an SQL. In an SQL, one can say create index I on R of A. So that means create the index which is named as I on the attribute A of the relation R. So for example, one can say create index B index on branch B name. And generally when only one attribute is being mentioned, it is the B plus tree index that is being meant. So that is the B plus tree index that is being meant. And simply one can also say drop index just to delete the index. That completes part about indexing, and we studied about hashing, static hashing and dynamic hashing, and some tree based indexing. So thank you.